Okay, so get this. You sent over this research paper about physics-guided neural networks,
Yeah.
PGNNs.
That's right.
And wow.
Yeah, it's pretty cool stuff.
It's like a glimpse into the future of scientific modeling.
It really is a potential game changer.
And the paper itself, it focuses on this very specific thing.
Okay.
Lake temperature modeling.
Right?
But when you think about it,
Yeah.
if we can accurately model something
Uh-huh.
as complex and dynamic as a lake's temperature,
Right.
the implications
It's
are
huge.
huge for things like climate change research.
Absolutely. Especially given your interest in all that.
Exactly. And what's so exciting about PGNNs is they address some of the fundamental limitations we see in these traditional modeling approaches.
Exactly.
Right?
Yeah.
Because on one hand, we have these powerful data-driven models like neural networks, and you know how those work?
Right. Amazing at finding patterns.
Yeah.
Making predictions.
Super powerful. But
they're a bit of a black box.
yeah.
Sometimes we don't always understand the why behind their predictions.
Yeah.
Which can be a little unnerving.
A little bit, yeah.
Especially in scientific contexts.
It can be a problem, that lack of transparency.
Right.
Plus,
Yeah.
when they're trained on smaller data sets,
Uh-huh.
these models can sometimes pick up
Okay.
on correlations that don't actually mean anything,
Gotcha.
which can lead to inaccurate predictions.
So, not ideal.
Not ideal, no.
Then on the other hand,
Right.
we have physics-based models
Yeah.
that are grounded in
Well, physics.
physics.
Yeah.
So they're generally more interpretable,
Yes, more transparent.
but they're also limited
Yeah.
by our current scientific understanding.
It's true.
Right.
The real world is messy and complex,
Uh-huh.
and sometimes our scientific understanding
Isn't complete.
isn't complete. Yeah.
So these models have to rely
Okay.
on simplifications and approximations,
Right.
which means they might not always capture the full picture.
Okay, so both approaches have their drawbacks.
They do.
That's where PGNNs step in.
Exactly.
Right. Blending the
And
strengths
that's the idea.
of data-driven
Yeah.
and physics-based modeling.
Right.
So tell me, how do they actually pull that off?
Well,
How do they actually do that?
think of it as building a neural network,
Mhm.
but giving it a solid foundation in physics.
Okay.
There are two main techniques at play here.
Right.
One is the use of hybrid physics data models.
Okay.
We start with a physics-based model,
Uh-huh.
which gives us some initial predictions.
Right.
Then we feed those predictions,
Okay.
along with the raw data,
Yeah.
into a neural network.
So it's like the neural network gets a head start.
Exactly.
It's not just wandering around in the dark.
Precisely. It can use those physics-based predictions as a starting point
Right.
and refine them using its ability to learn from data.
I see.
But here's where it gets really interesting.
Okay.
The second key technique
Yeah.
is the use of physics-based loss functions.
Okay. Break that down for me.
Sure.
What's a loss function in this context?
Essentially,
Yeah.
it's a way of telling the neural network how well it's doing.
Uh-huh.
In a traditional neural network,
Right.
the loss function focuses solely
Okay.
on how closely the model's predictions match the observed data.
So the goal is to minimize
Yeah.
the difference between prediction and reality.
Exactly.
Got it.
But with a PGNN,
Okay.
we add another layer to this.
Okay.
The loss function also penalizes the model if its predictions violate known physical laws,
Interesting.
even on data it hasn't seen before.
So it's like the model is being trained to not only be accurate,
Right.
but also to make sense from a scientific perspective.
Yes.
It has this physics tutor looking over its shoulder saying, nope, that doesn't fly.
Exactly.
According to the laws of nature.
That's a great way to put it.
Uh-huh.
This physics-based constraint ensures that the model doesn't just learn spurious correlations.
Right.
It's learning something fundamental about the underlying system.
This is all starting to click now.
Good.
And in this specific research,
Mhm.
they used lake temperature modeling
Yeah.
as their test case.
Right.
Why lake temperature?
Right.
And how did they actually apply these PGNN concepts?
Lake temperature is a great example
Okay.
because it's influenced by a lot of different factors.
Mm-hmm.
Sunlight, wind,
Yeah.
air temperature,
Uh-huh.
even the shape of the lake bed.
Okay.
It's a complex system.
So it's a perfect challenge for a PGNN to tackle.
Exactly.
Yeah.
They started with a widely used physics-based model called GLM
Okay.
to generate an initial set of temperature predictions for a lake.
Okay.
Those predictions,
Uh-huh.
along with meteorological data,
Okay.
were then fed into a neural network.
Right.
But here's the key. They incorporated a physics-based loss function It enforced a fundamental principle.
Okay.
The relationship between water temperature and density.
Because denser, colder water sinks.
Right.
Right.
So you would expect to see colder temperatures at greater depths in a lake.
At greater depths, yeah.
Precisely.
Okay.
They basically told the neural network, hey, you can learn for the data.
Right.
But whatever temperature predictions you make, they better result in a physically realistic density profile for the lake.
So they're essentially constraining the model's learning process.
Exactly.
With this physics-based knowledge.
Yeah.
That's really clever.
It is.
But did it actually work?
Well,
did the PGNN outperform
let's talk about it.
The traditional approaches?
The results were remarkable.
Okay.
Not only did the PGNN significantly improve accuracy in predicting lake temperatures, but it also consistently produced temperature profiles that made sense from the physics standpoint.
Okay.
In fact, it outperformed the purely physics-based model by 15%.
Wow.
And a standard neural network by a whopping 25%.
25% improvement in accuracy. That's huge.
It's significant, yeah.
Yeah, but beyond just the numbers.
Right.
What really struck me was how the PGNN nailed those subtle shifts in temperature.
Yeah.
You see as you go deeper into a lake.
Absolutely.
You know those distinct layers of warmer and colder water?
Yeah, those thermoclines.
Yeah.
Yeah, that's something that traditional models often struggle with.
Right.
They might get the overall temperature trend, right?
Yeah.
But they miss those finer details.
And those details matter.
They do.
Right. Especially if you're trying to understand things like how lake ecosystems respond to changes in temperature.
Absolutely.
Right.
And that's where the PGNN's ability to produce physically realistic density profiles is so important.
Yeah.
Because it's not just about predicting temperatures. It's about understanding how those temperatures translate into the physical structure of the lake.
So it's like the PGNN has this built-in BS detector.
Right.
For physics.
Yeah.
It's not going to predict something.
Exactly.
That would make a physicist facepalm.
It's going to get called out.
Huh?
Yeah. And the researchers really highlighted this by comparing the density profiles generated by different models to actual observations from the lake. The PGNN's density profile was practically spot on.
Wow.
Even at depths where there were no temperature measurements to go by.
Hold on. It was able to make accurate predictions, even in areas where it had no data.
Well, it's not that it had no data.
Okay.
It's that it was able to extrapolate based on the physics and the patterns that it learned from the data it did have.
So it's taking what it knows and applying it.
To make inferences.
Okay, so it had data.
Right.
But not complete data.
Not for every single point in the lake.
Yeah.
It is impressive.
It is impressive. Yeah.
And it speaks to the power of incorporating physics into the learning process.
The
PGNN wasn't just memorizing patterns in the data it had seen.
Right.
It was learning something fundamental.
Yeah.
About how water temperature and density interact.
Okay, so we've established that PGNNs are more accurate and physically consistent.
They are.
But what happens when you don't have a ton of data to work with?
That's a great question.
Because in the real world,
right.
we don't always have
perfect,
abundant data sets. Did the paper look at the impact of training data size?
They did. And this is where it gets really interesting.
Okay.
As you might expect.
Yeah.
When they reduced the amount of training data, the performance of all the models started to drop.
Makes sense.
Less data, less to learn from.
Yeah.
But here's the key.
Okay.
The PGNN was much less sensitive to these changes in data size.
Oh, interesting.
Even with a limited data set. It was still able to maintain a relatively high level of accuracy and physical consistency.
So it's like those physics-based constraints act as a safety net.
Yeah.
Preventing the model from going completely off the rails.
That's a good way to put it.
When data is scarce.
Yeah.
I like that.
And that robustness is a major advantage.
Yeah.
Especially in scientific fields.
Right.
Where data collection can be expensive or time-consuming.
Thinking about your work in climate modeling.
Yeah.
The fact that a PGNN can generalize well with limited data?
Right.
That's huge.
It is.
Yeah.
It opens up the possibility of building accurate models for regions of the world where we just don't have a lot of historical climate data.
Exactly.
Yeah,
so it's one of the reasons I'm so excited about the potential of PGNNs.
Me too.
They offer a way to overcome some of the data limitations we've been grappling with for years.
Absolutely.
This all sounds incredibly promising.
It is exciting.
But I'm curious. Did the researchers explore different ways of combining physics and data within the PGNN framework?
Yeah.
Like different hybrid model designs?
Yeah. They experimented with a few different approaches.
Okay.
And while they didn't find one magic formula that worked best across the board.
So no magic formula.
Right.
But they did find that tweaking those hybrid designs could lead to even better performance.
You could fine-tune it. Yeah.
Like fine-tuning the recipe.
It is a bit like that.
To get the perfect cake.
Yeah.
Right?
Sometimes a slight adjustment in how the physics and data are integrated can make a significant difference in the model's accuracy and efficiency.
Okay, so we've covered a lot of ground here.
We have.
We've talked about why PGNNs are needed, how they work, and we've seen how they stack up against traditional approaches.
Right.
But I'm itching to know more about where this all goes from here. What are some of those exciting future directions you mentioned earlier?
Well, one avenue that really gets me excited is pushing the boundaries of what kind of physics we can incorporate into these models.
Okay.
The lake temperature study used a pretty straightforward principle, water density.
Right.
But imagine applying PGNNs to problems involving fluid dynamics.
Oh, wow.
Like modeling ocean currents.
Yeah.
Or maybe even incorporating thermodynamic principles into weather forecasting models.
That's what I'm talking about.
Yeah, bringing in the big guns of physics.
Yeah.
Exactly. We could start incorporating equations like the Navier-Stokes equations, which describe fluid flow, or even thermodynamic equations that govern heat transfer.
Wow.
Imagine the level of detail and accuracy we could achieve.
It would be a whole new ballgame for scientific modeling.
It would.
Yeah, but I'm guessing that comes with its own set of challenges.
It does.
Those equations are notoriously complex.
They are challenging.
Yeah.
But I think it's a challenge worth tackling. The potential payoff is enormous.
Yeah.
And remember, PGNNs are all about combining the strengths of physics and data science.
Right.
So as we develop more powerful computing resources and algorithms, I think we'll be able to handle that complexity.
So it's like we're pushing the boundaries on both fronts. The physics we can incorporate and the computational power to handle it.
I like it. Yeah.
Okay. What else is on the horizon for PGNN research?
Another exciting direction is exploring different types of neural network architectures.
Okay.
The lake temperature study used a relatively basic feed-forward network, which is kind of like a one-way street for information.
Right.
But there's a whole world of other neural network architectures out there.
Yeah.
Each with its unique way of processing information.
Okay, like those convolutional neural networks I've heard about?
Yeah.
The ones that are really good at image recognition.
Exactly. Convolutional networks are great for spatial data, like images.
Right.
But they're also recurrent networks.
Okay.
That excel at handling time series data.
Like weather patterns or financial markets.
Exactly.
Yeah.
So a big part of future research will be figuring out which architectures are best suited for specific scientific problems.
So it's not a one-size-fits-all approach.
No, it's not.
You have to match the neural network architecture to the type of data.
Yeah.
And the problem you're trying to solve.
Exactly.
Makes sense. Is there anything else you think is crucial?
Yeah, one thing that's often overlooked, the interpretability aspect.
Okay.
Even though PGNNs are more interpretable than traditional neural networks, there's still room for improvement.
Right.
We want to be able to peer inside these models and understand why they're making the predictions they do.
You're right. It's not enough to just have accurate predictions. We need to be able to trust those predictions and understand the reasoning behind them.
Absolutely. And that's where techniques for visualizing and interpreting the inner workings of PGNNs become really important.
Okay.
It's an active area of research. And I think it's going to be key for building trust in these models.
Right.
Especially in fields like medicine or climate science.
Right, where the stakes are high.
Where the stakes are high, exactly.
This all sounds incredibly promising.
It is.
It feels like we're just scratching the surface of what PGNNs can do.
I think so.
So before we wrap things up, I have to ask.
Yeah.
What's that one big thought-provoking takeaway you want our listener to walk away with today?
I want them to consider this. What if every scientific model, not just those used in specialized fields, was built with this inherent understanding of physics?
Interesting.
What if accuracy was just the starting point?
Okay.
And scientific consistency was the ultimate benchmark?
Okay.
How would that change our understanding of the world and our ability to solve complex problems?
Wow, that's a powerful thought.
It is.
It really makes you realize that PGNNs represent a fundamental shift.
I think so.
In how we approach scientific modeling, it's about moving beyond black box models.
Yes.
And building a deeper understanding of how things work.
It's about creating models that are not just predictive, but insightful.
Well said. And to our listener, we encourage you to dive deeper into this fascinating world where data meets physics.
Absolutely.
This deep dive is just the beginning. Who knows what incredible discoveries lie ahead?
Who knows?
As PGNNs continue to evolve.
Very exciting.